Good morning. As I just said before I started this recording, welcome. I thought since the sun is out, I'll change it up a little bit. I'm on my back deck. You can see, if you're familiar with the South Coast, you can see Saddleback Mountain in the background. I think there's a few more people joining. I wasn't actually expecting that the glare was this big, so you'll see me squinting a little bit. I am recording, so we're all good. I've got the chat line up. Let's put this to the side. I'm going to close that. Okay, so as you might have, well, hopefully you are aware that we have our online assignments that are happening. So they opened on Monday, 1 minute after midnight. It will close this Friday. It is 5 questions. I don't expect that you will have too many issues with that. That will be the same for next week. Assignment 2, same thing. It's only 1 attempt, but it is not timed and it is completely open book. So and they're worth 5% each from memory. In week 11, we'll have a couple of opportunities for face-to-face interactions. I'll be running 4 workshop. Well, we've been calling them lab experience. What it really is, it's an opportunity for you to come along and work on the concrete report and look through all the videos. So everything will be online in terms of the experiment, but I will be there with a number of demonstrators to help you getting your report started, and you can ask me any questions you like on the report. And they'll also, I still have to put this up, but I'll also put up the marking scheme. But that will hopefully become clear in the next few days. And we are at the back end of the session. This is week 9, so there's only this week, so today, next week, and then week 11 we'll do some lectures. In week 12 I'll do another exam training session where we work through problems, and then in week 13 we will have the end of session test. So there's no final exam for this subject. You will be done and dusted with CHEM103 by the end of week 13. The end of session test will run in the same format as all the other assessments that I've done. It will be open book, and it will not be timed. You'll see me squinting because the sun is quite hard. So I received, as I said last week, there was an issue, not an issue, but question 10 wasn't actually from the mid-session test, wasn't actually looking for the sign. So if you included the sign, you wouldn't have received full marks. I've now gone through everybody's results, or at least those of you that got it incorrect based on the exam, and I've updated. And thank you for everyone that emailed me. I think I've responded to everybody, and you can check your marks on Moodle, but that should all be updated at the moment. However, if I did miss someone, then please have a look and get in touch and let me know. So safety in the labs is something that I've always been talking about, and I know we've done all of our actual laboratory, like where we're handling chemicals. But last year, I just wanted to bring this up. Last year, there was an incident at UOW in a chemistry lab where a couple of students were exposed to an acid solution. So even if you are wearing PPE, and these students were all wearing appropriate PPE, that doesn't give you a carte blanche for when something goes wrong. PPE only protects you in certain bits. You know, if you do get exposed to something, then that can still have adverse effects. So it's just a first line of defense is probably the best way to think about when we talk about PPE. So the students, most of them were treated on site, and then it obviously went through a safe work procedure. And I think I wasn't involved in the lab, but I think after that there were a few updates made in the way that certain assets were handled. I just thought I'll put that in there, just to always be aware that your PPE is a first line of defense. It's not gonna give you full protection for when something happens. You always need to just practice your safe work procedures. So just to go on and finish a couple of things from last week, and I am going to have to put my sunnies on because the sun it's about to go behind a big gum tree, or that's a turpentine tree. So hopefully it go behind there. I can actually see a bit better. I didn't think about this, where the sun was going to be. We talked about these orbital structures last week. I just want to continue a little bit about that. We saw in particular where we have combinations of s and p orbitals that give us sp orbitals that you can then use, for example, that dominated in HCl, beryllium fluoride, and that really result in linear molecules. If you get an S and two P's combining, then you can end up with 3 sp2s, and the sp2s are the one that are very crucial for those engineering materials that I've been talking about: graphene, carbon nanotubes. It's also in graphite, it's in diamond. And then you get this sort of planar type of structure. And then if you go to the sp3, which is what you would normally get at most carbon materials, or methane, ethane, all of those will have these particular type of sp3 bonding, is where one of the s orbitals combines with three of the p's. And then there's also, this then leads you in, because somebody asked, what is the real, what is actually this all leading to? And it actually leads to an understanding of bonds, because you can use these orbitals to understand the bonding behavior. So we have double and triple bonds. We generally talk about, and you may come across this, where they talk about sigma bonds, indicated by the Greek symbol sigma, of course, and pi bonds. And that has to do with the way some of these materials are bonding. So in particular, a sigma bond is generally like you have a head-to-head overlap. So here you have these lobes coming out from these electron orbitals. And bear in mind, all of these electrons, these lobes that you're seeing, are really showing you the probability of where the electrons can be. And there's usually a symmetry involved with this. So pi bonds are generally, you have this type of sideway overlap. So it almost, and it's a bit hard to see on this axis, but it indicates that you have an electron density that is sort of lying above and below the internuclear axis. So here's the axis of your molecule, and then these pi bonds, they sort of hang above and below that, where the sigma bonds are on this particular axis here. So in general, what we can state is that if you have a single bond, so think a hydrogen connected to a carbon in a methane molecule, that is always a sigma bond. However, if you have multiple bonds occurring, then they will all have one sigma bond, but they'll also have these pi bonds. So if you look here, for example, if you go to a C double bonded, then you will get these different types of arrangements arising. So we have a carbon here, and we have all these sigma bonds, and you can see that they're lying outside the plane of the internuclear axis. Again, you don't really need to understand how these come about. Just be aware that you can have sigma bonds and pi bonds, because they can have an impact on the behavior of material. So for example, if we talk about this engineering material called graphene or carbon nanotubes, they can sometimes stack on top of each other, like putting sheets of paper on top of each other. And that is sometimes referred to as pi stacking, or pi-pi stacking is where you get the stacking of the pi-pi bonds that are responsible for how these materials interact. And that's exactly here what I mean with this pi stacking. So if you have another layer of this on top of it, then you can get this pi stacking. The other interesting thing with these electrons, if you have bonding electrons, so between these materials, and it can be either a sigma or a pi, and if they are completely shared between, let's say, two atoms in a molecule, then we would call them localized, because they're really specific to a particular area in that molecule. Now, when we get to these engineering materials, or engineering nanomaterials, I should say, like carbon nanotubes and graphene, which you may come across, there we can't really talk about localized electrons. They're really in what is called a highly delocalized state. And that delocalized state is important for the exceptional electrical behavior that you can get out of these carbon nanotubes and graphene. So the measurements have been done on these materials, and their electrical conductivity, if you're familiar with that concept, can be the same as for metals. So carbon nanotubes and graphene, which are made out of these carbon materials, they have such a good electrical behavior that they compete with metals. So, and that's this concept of delocalized electron. It's not that the electron that's here is just whizzing around is probably not the right way. So if we look at this, what we actually mean by delocalized bond, this is where you get this pi bonds, which are formed by these sp2 hybridized orbitals. It also has, because it's sp2, it has another p orbital left. And then these p orbitals, you get these type of resonance structure, because there's a 6-membered ring. There are 2 ways in which you can organize these shared p orbitals. You can see this one here, where there is a this localized pi bond is on the left-hand side, on both the left-hand side and the right-hand side. Or it can be, if you switch it around, it can be here at the bottom. So there are a couple of ways in which you can do that. And because that happens, that's what's called a resonance structure. So it's resonating between different types of these localized pi bonds, and that gives us this delocalized pi bond. And that's usually represented by this sort of circular arrangement. So when we actually write this, and you may come across this in the molecular structures that you'll see, you'll have on a molecular level. So here is the structure. We have benzene, so we have 6 carbons, 6 hydrogens. We have 3 double bonds. And because there is that much symmetry in the molecule, you can either, let's say, if we call this carbon 1, you can have the double bond on carbon 1 and carbon 2, or you can have the double bond on carbon 1 with 2, 3, 4, 5, 6. So the structure itself can switch in between that. Another way of representing that is removing the hydrogens, because we usually know if there's no dash here that we implicitly assume that there's a hydrogen there. We put these double lines there to indicate that that's a double bond. We have this equilibrium structure here because it's resonating between the 2 different forms, or a more general way is just indicating this with this circle, this sphere in the middle, which indicates that we're a delocalized bond. And you will see this, like I said, a lot of times in the molecular representations of these molecules. So this information that we have, and this, I believe, is a picture of the Atonium, if I think it's the correct term, in Brussels, in Belgium, in Europe. So the information that we have about molecules and the way that they're interacting, we can use that to really explain different types of behavior. And with different types of behavior, I mean rheology. So how easy does something flow? How conducting can something be? Is something going to be miscible? Is something going to be able to mix? How strong are these bonds? All of that information you can get insights from if you look at the molecular picture. So we generally connect the molecular state with the macro scale that we see around us. And that's also what we did in entropy. We relate the number of microstates. So we look at the molecular level or the microstate level, and we can relate that to properties that occur on the macro state. It's a very interesting area if that's your cup of tea, cup of coffee, or whatever your favorite beverages. We already looked at intermolecular forces as part of our workshops. And we know that if you look at interactions between molecules, they're generally not as strong as if you're trying to get an atom out of, say, for example, hydrogen chloride. If you wanted to get an atom out of that bond, you got to put a lot of energy into that to break that bond. But to put two molecules out of each other, to separate two molecules, that's a lot weaker. And this is what I mentioned before. If we know information about these intermolecular interactions, which you did as part of the workshops, then we can say, you can get some information about, is this going to be a high melting material, like high temperature? Is it going to have a lot of surface tension or low surface tension? Is it going to have a high boiling point? So the stronger the molecules are tied together, the higher a boiling point will be, for example, because boiling point means you got to get the molecules to escape from the liquid phase to the gas phase. So they have to come out of this arrangement where they're all in their liquid phase, and then they have to go to the gas phase. So they really have to do an escape. They have to escape from the rest of the body that is still in the liquid phase. And these we already talked about, the states of matter. So we can have gases, we can have liquids, and we can have solids. And really what that indicates, it tells us a little bit about the strength of the forces or energies between them. In the gas state, we don't really have a lot of the intermolecular forces. As we're condensing the material down, and sometimes liquids and solids are talked about as the condensed matter state, because you're literally condensing it down either from gas to liquid or from liquid to solid, then these more intermolecular forces start becoming increasingly important. So the strength of the intermolecular forces actually increases from the gas to the liquid to the solid state. And then you obviously, if you put temperature in it, you can't probably see this, but I'm sitting in the sun and I'm pretty hot. So temperature heats everything up. The gas molecules around me would also be moving at an increased speed to when I first got up this morning, when it was only 12 degrees here. I think it's probably in the sun. It's a bit warmer at the moment, but the kinetic energy that gets put into there from or that is related to the temperature also dictates how fast things move around. One of the other aspects that we instinctively know, and there's a little video that I put up last year when it was absolutely bucketing down with rain, when the stable was still inside the house and not outside the house. But one of the things instinctively, ice will, no matter what you do with it, as long as it doesn't melt, it will retain its own shape. You can put an ice cube in a beverage, and for a while you can see that the ice cube is there. However, water is very different. Water will always take on the shape of the container that it's in. You can't see this. This was my coffee cup. I've got a bit of water in here. When I pour it, it takes the shape of the container. And that is a very important difference in the properties of these matters. Ice retains, so a solid retains its shape. You can walk on it as long as the ice is thick enough. However, water, you cannot walk on water. Many people have tried. There's probably a theoretical possibility that you can walk on water if you have enough speed so that you actually get beyond the relaxation motion of the water molecules, but that's a totally different story. So One of the nice things, of course, about water for people that are hopelessly addicted to surfing like myself, but are not very good at it, is that water flows. Water has a flow. That also means it has a wave action and you can surf on it. Ice does not flow. On the other hand, if you're familiar with ice, we don't get ice that often around us where we live in Australia, but it's very solid and it is incredibly hard to surf on. It is probably near impossible to surf on. What is much easier to do on ice is, of course, skating. I grew up in the Netherlands where in winter we sometimes get -14 to -20 centigrade sometimes, and then all the lovely ponds around us will freeze. So I grew up in the winter, we would always go ice skating, you know, and as long as nobody falls through the ice, it's a really fun experience. And there's a lot of physics involved, a lot of chemistry involved as well, that has to do with the friction and the pressure that you put onto this, but that's a completely different matter. From an engineering point of view, both surfing that uses a liquid state of matter and skating, and for example, snowboarding or skiing, whatever you're into, they are very interesting from an engineering point of view in the way that you know the interactions happen between the items that you're using here. You're using a solid skate that goes onto the ice, and then there's all kinds of stuff, friction, really interesting material. And if we look at what the characteristics of the states of matter are, we know that a gas, for example, will, if we put that in an enclosed container, it will immediately completely fill the volume, and it will also take on the shape of the container, right? If we have an evacuated cylinder and we let gas into that, then it will try to fill the entire container. Liquid will assume, you know, only a part of the container that it occupies, unless of course you fill it right to the top. Whereas a solid, ice cubes, they just maintain their own shape and they maintain the volume. So gas expands, liquid does not expand, and solid does not expand. Gas you can compress, right? We know this when you do something as simple as using a hand pump to blow up your tires, that you are actually compressing the gas as you're pushing this down, and that creates this pressure flow that it then goes into your tire. It also generally, you lose a bit of the interaction with the heat because you can feel that bottom of your pump is going to get hot. Water, you know, anybody that has ever fallen from a height onto water, even if you do a belly flop into a pool, you know that is completely incompressible. If you're surfing, for example, and you stack it, let's say I have tracked takeoff speeds, you know, 40, 50 kilometers an hour. I know the big wave surfers go a lot faster. If you stack it at that speed, let's say 30 kilometers an hour, 40 kilometers an hour, water is very incompressible. You can literally bounce along the surface of the water because you can't penetrate it. That's probably not really what they're meaning with compressible here. What they mean by compressible is if you have water, you know, in a particular cylinder and you try to compress it into a smaller volume. What I was talking about is obviously penetration, but incompressibility deals with if you're trying to have a volume of water and you're trying to compress the volume. That's pretty much impossible. With a solid, it's also impossible. We know that gases really flow easily, really easy. Water, you know, as I will demonstrate, flows really easy. Solid, in the definition of it, it really does not flow. And then we know, you know, if you're doing some nice cooking in your kitchen and somebody walks into the house, they will immediately can really smell your nice cooking flavors, and that means that that's due to the diffusion in a gas goes really fast. In a liquid, it goes a lot slower, which you can demonstrate, but if you put a little bit of food coloring in a glass of water, you'll see unless you stir it, it takes a bit of time. And in a solid, it's on a totally different scale. So that brings me to one of the quirky facts from today is people have, they've wondered about cats. Are cats really classified as solids or as liquids? So if you look, for example, and the question is, and this is a very serious study, by the way, that was done, and I'll show you the reference of the paper in a bit, where somebody asked the question, are cats really classified as liquids or solids? And there's a little video where you can see a cat going into a glass body, and obviously the evidence, and this was also part of an article that appeared in The Conversation, because it was a person that wrote an article that won them the IG Nobel Prize, which is for quirky science, are cats liquid? So in this case, they use this, for example, as the evidence. Here we've got a cat, and it's almost perfectly fitting inside the sink. So what they're assuming is, liquid, it behaves like it assumes shape or portion of the container that it occupies. And again, you've heard me probably many times talk about this. The experiment that you're looking at isn't really important. It's you can apply all the concepts that we're talking about to the world around us. Now, the cat is probably a very, very quirky thing, but somebody, this Mr. Fardin from France, wrote a very, very lengthy, he says in this letter, I highlight some of the recent developments around the rheology of Felis catus, but it's a very, very long paper that he wrote as a celebration. He obviously, I'm actually assuming it's a man, but I don't know that for sure. So this scientist had obviously a lot of time on their hand, and they did a long investigation about liquids and solids. And in particular, if we talk about liquids and solids, you can look at the rheology. And rheology is really how fast does something flow. That can be characterized by something that is called the de Boer number. If you're doing engineering, depending on what form of engineering you do, you will come across different types of numbers. One of the, for example, if you're looking at flow behavior, you will have the Reynolds number. In this case, they're talking about the de Boer number. So dE is equal tau divided by T, where tau is the relaxation time, or you can think of this as the rate of expansion, and T is the duration of the experiment. So if T is a really long time, so if the flow is happening over an extremely long time, then we know that a de Boer number is going to be a lot smaller than 1, which means that it's more behaving like a viscous or a fluid. So think, for example, the flowing of peanut butter, think of concrete, for example. If the duration of your experiment is really short, then it will behave more like an elastic or solid, and in this case of the Boer number is much larger than 1. So, for example, if you do a short experiment, the classic example in this is potty, silly potty, that my kids play with this, and it's a fascinating material. It also does a lot of self-healing. But let's say if you bounce a potty ball, then it would generally, it's a very short experiment, and then the time is really short, so our de Boer number is much larger than 1, and we know that it bounces. However, if you take the potty and you put it on a table and wait a day, 2 days, eventually what you will find is that your potty will have completely lost the shape that you've put it in. So let's say you roll it, you massage it into a ball. If you leave it long enough, it will lose its complete structure. And that is when we now have an experiment over a long time, so 24 hours or more, then the Boer number is now much smaller than 1, and it actually behaves like a viscous fluid, and then it flows. Now, the reason why I'm talking about this is that this person, the scientist called Jardin, actually examined this and looked at cats jumping around. So this person analyzed, I don't know how many YouTube videos, and observed cats And then he or she came to the conclusion that if you have this shorter time and the cat jumps, it behaves more like a bouncing material. If it's over a longer time period, so as long as you give the cat enough time, I've got 2 cats and a couple of dogs running around here. If I give my cat long enough time, I find these cats in very, very strange places where they're curled up inside things. Just here, like you see, this cat here is having a bit of a snooze in a wine glass. And I should also point out that, and this person in this article is stressing at all times that, you know, there were no cats harmed in these experiments. They were all doing on natural observation. They didn't actually needed clearance to do animal experiments. So the other bit that they look at was flow behavior. So we all know if you use toothpaste, it's a material in there, you need to squeeze it, or you need to squeeze your ketchup bottle in order for the material to flow. And that has to do with something that is called yield stress. That's also a very good thing, because that means you can leave your, like my children do, you can leave your toothpaste open and it still takes a little bit of time before this to dry up. But if you squeeze it, it will only flow if you squeeze it. The person in this paper used this example here of this cat in a glass bottle, that the cat will not flow unless it's actually had a yield stress applied to it. So, you know, dogs are obviously very different. This is one of my dogs. They show none of this behavior. This only refers to cats, of course. And I just put this example up so that you get an idea that you can use whatever we're teaching here and apply it to the world around you. Obviously, the cats is a very quirky example, but hey, why not look at a few quirky examples? The bit that we're going to talk about the rest of the time is to look at gases, which really deals with chapter 10 in this book and relates to matter on the molecular scale. What I'd like you to get familiar with is gas pressure, carrying out these pressure calculations with unit conversions. There are that many different units of pressure. You know, there's so many different ones around. And then you can also then, I'd like you to be able to apply the laws, the ideal gas laws. And it looks like there's a FedEx guy that is going to come and try to deliver something. I just saw him turning up there. So we'll keep going. Oh no, he's just turning around. He went the wrong way. Google sometimes sends people up where I am and not the way they should be coming. So I'd also like you to be familiar with this kinetic model, and then also think about how this kinetic model applies to things like temperature effect and diffusion, or possibly also effusion. Effusion means there's materials coming out. So a couple of things that we know about gases. We know that the physical properties of gases, you know, they're in a gaseous state, that they're all pretty similar. We know also that they really have low molar gases. If you think of nitrogen is about 28 grams per mole. If you compare that with some of the large polymers, that's a lot more. If you think of oxygen, O2, that is 32 grams per mole. And like we just looked through, we also instinctively know that they have extremely low densities. And that's obviously, I can do this, which is very easy to do. I'm pushing some of the gas molecules apart. And that is due to there's not a lot of density. So there is some force working on me, but it's a very low density. And you can compress them down. And then 2 or more gases form if you put them together, they usually form a mixture. And here is, just have a little visitor here. So some of the gases that we talked about, we've already come across some of them when we talked about the World War I's. Some of them are good, some of them are not so good. Carbon dioxide we get around us. Carbon monoxide is pretty bad. You can't smell it and you can't see it. Methane gas is also generally colorless, says it's odorless, and it's obviously highly flammable. You also have a gas called ethane or ethylene, C2H4, which again is colorless. You get the picture here. It is generally, these gases are very much colorless, except possibly this nitrogen dioxide, which is red brown. And then we get these really bad ones, the hydrogen sulfate, which comes out of volcanoes a lot, hydrogen cyanide, which is very bad. So if you smell ammon's, that's generally a bad sign. So if we look at, we go to how do we actually define a sample of gas. We know it needs a temperature, it has a pressure, there's a volume involved. Usually we have an amount of gas that has a number of moles. So we still need to define pressure. This is probably all very familiar to you, but I'll just go through it in case it's not familiar. Pressure is really a force applied to a particular area. So it's a force F divided by cross-sectional area A. The atmospheric pressure is generally the weight of air per unit area. So we feel a pressure that is exerted by all the air that is above us, and that gives you this particular type of pressure that you feel. The pressure obviously changes where you are with respect to the height of the Earth. And then here's come some of the confusing bits. So we can either use, if we go to SI units, we use the pascals, which is named after this French mathematician. 1 Pascal equals 1 Newton per square meter. We also use bars. 1 bar is 10 to the 5th Pascal or 100 kilopascals. We also have millimeters of Hg or torr, and that has to do, is measured by these sort of barometers. And then if we look at just the atmospheric pressure around us, 1 atmosphere, which is generally what is referred to as being at sea level, is 760 torr, 760 millimeters Hg, 101.325 kilopascal, and and that's also then equal to 1.10325 bar. So beware and be comfortable in converting these. I'm pretty sure if this comes up, you can obviously just go onto Google and say conversion, and there'll be all these websites that you can find where you can do conversions. But you might also occasionally have to do your own calculations. This other device here called a manometer, which looks at, you have a gas, there's a little bit here, it has an open end, there's a fluid in here. So depending, and then you've got the pressure of the gas, and the cylinder is pushing down from this end. It's going to try to push this column of liquid out, whereas the atmospheric pressure is coming in and is going to try to push the liquid that is in here on the other side. So if you calibrate these, then you can figure out what the pressure is of your gas. So it then relates to, you can just calculate from the atmospheric pressure plus the pressure of the height difference between these two different types of liquid levels. The standard atmospheric pressure, which what we just talked about, it's 1 atmosphere, 760 torrs. And if you've ever watched a balloon, we know that if you have a fixed volume, we've already seen this before, if we change the temperature, so if we increase the temperature, the pressure, so we put more energy into the gas molecules, then our molecules will want to expand, they want to take up a larger volume, and that means the balloon expands, and then the balloon rises up into the atmosphere. We can also look at something that is called Boyle's law, which deals with the pressure times the volume is a constant. And that really allows us to calculate if we have two different conditions, so we have an enclosed form of gas, we have it at pressure 1, it will occupy volume 1. If we change it to the pressure 2, so let's say we increase or decrease the pressure, then we know that the volume has to change. So if you actually calculate that V versus P, you get this sort of not straight line. However, as you can see in this formula, if we do the volume versus 1 over P, then we generally get a very nice linear relationship. And that's what I've just said. You take a balloon, you heat it up, it will expand. You cool it down with some ice cubes, and then it will start to deflate. And that's assuming that you don't miss any materials coming out of it. There's also a couple of things like Charles's law, where now we know that the volume is equal to a constant times the temperature. So these are all different laws that have been coming up, where you can compare different types of conditions, all assuming that you're not adding or taking materials out of it. And again, you can then, if you plot this in the correct way, you can get these straight lines occurring. Another one that came up is related to Gay-Lussac, which means if we have, as long as the temperature and the pressure are constant, the volume of gases that will react with each other was always in whole numbers. We've already talked through some of these concepts because it's really based, as it says here on this third line, it's based on the stoichiometry. And this figure, you can see that we know, if we go to Avogadro's law, we know that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. So this is an important law to realize. If we are at standard temperature and pressure, STP, then it doesn't matter what gas we have. If it's 1 mole, it will occupy 22.4 liters. So if we take helium and we have 22.4 liters, we are at 1 atmosphere, 0 degrees. The mass is 4 grams. If we now take nitrogen and we have 1 mole of gas, which is 6.02 times 10 to the 23, which is Avogadro's number, we know that nitrogen will also occupy 22.4 liters, but it has a different density because nitrogen is a much heavier gas. If we go to methane, CH4, and we take a mole of that, and we do that at standard temperature and pressure, so 1 atmosphere, 0 degrees centigrade, then it will be the exact same volume will be occupied. It's always 22.4 liters. So that is going to lead us to something that is called the ideal gas equation. Volume is proportional to 1 over the pressure. Volume is proportional times the temperature, which we already instinctively know. Volume is proportional to the number of moles. If you combine these, you get something that the volume is really proportional to the number of moles from Avogadro's law, the temperature from Charles's law, and the pressure by Boyle's law. So as this is a proportionality, we need to put in a constant to make this an actual equation. So we want to remove this proportionality and put an equal sign there. So what people came up with is to use this constant of proportionality R, which is also known as the ideal gas constant. So, and that leads us then, if we then bring P to the other side, we get to the ideal gas law. P times V equals nRT, the ideal gas law. So as we already had all these different units, it is going to be little surprise that the gas constant is in various different units around, depending on what you like. If you like to work in torrs, then R will be 62.36 a liter torr per mole Kelvin. If you work in calories, then it will be 1.987 cals per mole Kelvin. The ones that we usually work with if we go to the more SI units is in joules per mole Kelvin. And then it's 8.314. It's for some reason one of the other constants that no matter how hard I try, I still remember this by heart. So, and that gives us then this ideal gas equation, P times V equals nRT. We've mentioned the name a lot, but we haven't really talked about who Mr. Avogadro was. He lived in the 18th, 19th century. He was another example of somebody that did science in his spare time. It wasn't really his main occupation. He was really practicing law. But then I think there's this reference here that you can read more about it. Initially, he worked on high schools, and then he got a chair of mathematics at the University of Turin, which I believe is in the north of Italy. And one of the things he did was to introduce the metric system. So where people went away from all these different forms of non-metric things that we have, and then went to a fully metric system. And his main contributions have been, apart from that, the number of moles is named after him. He also had, his main work was on volumes and gases and temperatures of gases and pressure. So we can use the ideal gas law to also start defining the density of our gases. So we can have number of moles divided by volume equals pressure divided by RT. So here we just rearrange the ideal gas equation. We know that if we do the number of moles times the molecular mass, where the mass is in grams per mole, we get mass. So we can multiply n times the molecular mass, not to confuse here with the molar concentration, equals m is mass. If we now rearrange this, you do a couple of mathematical rearrangement, eventually you end up that the density is equal to the molecular mass, the molar mass, times the pressure divided by RT. And if that doesn't make sense, run through the calculations. There's a few steps missing here, but that eventually should all nicely fall out at the end. So then, as a quick recap, the only thing you really need to know is information about the molecular mass, and then the pressure and the temperature, and then you can calculate what the density is. The ideal gas law also gives you an opportunity to find the molar mass as long as you know what the mass, volume, and the temperature of the gas is. I've just moved over a little bit because the sun is pretty fierce at the moment. So if you want to combine, we can have gas data, that will give us pressure, volumes, number of moles, gas constant, and temperature. Then we have moles of another reactant and product. As long as you have a balanced equation, we can then get some answers out of it. So you can do calculations with these. Another law that is important to realize is Dalton's law of partial pressures. So as long as gases are not reacting with each other, if you then combine two gases that will not react, so think if you combine, let's say, two noble gases, say helium and argon, if you put them together in a container, they're non-reactive gases, they're really not going to react with themselves. So then what that means, if they're not reacting with themselves, you can then calculate the pressure of these, because it's going to be equal the sum of the pressures that each of these would do if it was just by itself in these containers. Or in other words, the total pressure is then the pressure of gas 1 plus gas 2 plus gas 3 and so forth. But again, this only applies if the gases are not reacting with each other. If they are reacting, then that becomes a different matter. If we have a mixture of gases, we can use the ideal gas law to also work out what the mole fraction is. So let's say you have a gas A and a gas B, and you want to find out how much you have of gas A over gas B. So as long as you know the number of moles of your gas, the total number of moles, you can again use the ideal gas law, because we know if you have the pressure of 1 over the total pressure, you can then use the ideal gas law to work out what the ratio is of your moles. Because if you're in the same volume, volume is the same, you're going to be at the temperature, that's a constant, so everything disappears and you just get this nice ratio. And that's usually referred to as the mole fraction. So the moles of compound 1 divided by the total moles. And the end result then is that you can write this as, you know, the pressure of 1 equals the mole fractions times the total pressure, or P1 equals X1 times total pressure, and that gives you the partial pressure. If we now go on to kinetic theory, you know, the laws, and this is important to realize, the laws are really been referred to as an ideal behavior. A lot of it that we observe in the world around us is not going to be ideal, and that's what some of this molecular theory is also going to help us try to explain. So the main points of this is a gas that is around us, like where I'm sitting and where you're hopefully sitting or maybe standing, is that gases are continuous and they're also in very much random motion. If we would take all the volume that is occupied by these molecules around us, the total volume that is occupied by the molecules is really small compared to the volume that we're actually in. So the actual amount of gas is not very large. And you can see that when you condense materials down. One crucial aspect here is that attractive and repulsive forces between gas molecules are negligible. That's obviously not entirely true, but you can do that in terms of the molecular theory. So we're just making a number of assumptions. Now, because they're all moving around, we know that there's going to be collisions occurring. Now, they're also constantly going to bump into each other. And we know then that energy, if you bump into something, there can be transfer of energy, but the overall kinetic energy is not really going to change. But that is obviously dependent on keeping the temperature constant. And we already know that how fast molecules move around is completely proportional to the temperature that you have around here. I've got about 10 slides left of this lecture, so I'm going to go a little bit longer than 10, probably say maybe not 5-10 minutes or so. So how fast do molecules actually use? You know, they're going pretty fast. If you look at this diagram here, this is the fraction of molecules. This is the molecular speed in meters per second. At 0 degrees, you know, they're moving still. The average speed is still somewhere in 500 meters per second. That's pretty fast. If you want to go from meters per second to kilometers per hour, you have to multiply by 3.6. So that is whatever, 1800 kilometers an hour. That's pretty fast. You know, and there's obviously, if we then increase the temperature, then that whole curve is going to shift to the right because we're putting more energy into it, which means the molecules are moving a lot faster. So the figure here that you can usually see is you get 3 different types of thing. You get the speed that is exhibited by the largest. So most molecules are probably going at about 500 meters per second, but some are going slower, like down here, and some are going a lot faster. Some might be going at twice the speed. You can then use this to calculate the average of all of them. And then you also have the root mean square speed, which is the one that we associate with the average kinetic energy, which you would calculate from the average kinetic energy. So we know, so the speed of the root mean squared is actually equal, if we're assuming 3 dimensions, by 3RT divided by the molar mass. So if we increase the temperature, the root mean speed goes up. If we increase the mass, the root mean square speed goes down. So heavier molecules generally move a lot slower. And that, you can see that's obviously determined by looking at experimental evidence. So here we've got molecular speed. Oxygen is 32 grams per mole, 28 grams per mole, 18 grams per mole, I think 4 grams per mole, and that's 2 grams per mole. So helium goes exceptionally fast, right? Or hydrogen, it is about 2,000 meters per second with the largest proportion, whereas oxygen goes a lot slower. It's somewhere around the 300. So if it has a lower mass, it will go a lot faster. These two concepts here that we talked about, everybody's familiar with diffusion. You cook something nice, you will smell it, and that has to do how something spreads through it. And that, as you can see here, has sometimes been referred to as the walk of a drunken sailor. I'm not sure if that's still appropriate, but it's not a straight line, it's a random approach, and that deals with if you have a substance there, it's going to get collisions and it's going to push into different directions. Effusion is if you take a cylinder and you allow the gas to evacuate through it. The best example of that is obviously a deodorant spray. You press it and then you actually allow it to come out, but that's really what is happening. It's effusing. It's, well, spraying, but it's effusing out. That's probably the closest I can think of it. Or again, you can, but that's actually evacuating. So forget what I said about the deodorant. That's not the really bit, because it needs to go into an evacuated space according to the definition. But the principle is roughly the same. We already know, we talked about the root mean square. So heavier gases move slower than lighter gases. That also means that if we have effusion happening, that the lighter gas will effuse faster. In these two pictures here, we've got helium, which is much lighter than argon. They're both noble gases. And then obviously, if we observe these over time, the helium balloon will go down a lot faster. Now, I mentioned this was the ideal gas law. In the real world, gases don't behave like ideal gases. They probably do, in the conditions that we're at. But as soon as you start to slightly range the pressure, they behave very different. And you can see this here. Here we got PV/RT. If that equals 1, we're an ideal gas. But if we start changing the pressure, they all start behaving very differently. And the reason for that is, gas molecules do have, they have a volume. There are, if you start compressing them together, they are going to feel their attractive and repulsive forces, because if we go and increase the pressure, you're going to put them in closer contact with each other. And that then means that's where this deviation comes around. However, there are various bits that people have come up with in the last 150 years to simply adjust this. So you can take this ideal behavior into account. The one that we use a lot comes from a person called van der Waals equation, or Johannes van der Waals. And it's really, what it does is it takes into account that you can get these attraction and repelling forces as you bring the gases in closer contact with each other. It looks a bit like P plus n squared A over V, so you can still recognize P times V equals nRT. So if these gas constants, which is A and B, if they are 0, then this completely goes back to P equals V times nRT. And there are other gases here. From the value of these numbers, you can see how much they're deviating. Helium, it's probably, well, hopefully it is of little surprise that the noble gases, who really don't have a lot of interactions with each other, are the closest to this ideal gas behavior. Helium really has very small correction factors. Carbon dioxide or even chlorine or water has very high correction factors. So there will be differences occurring. If you're wondering about Johannes, a lot of people will probably pronounce him as van der Waals, but it is actually van der Waals. If you into your music from the 70s and 80s, you had Eddie and Edward Van Halen, or from Van Halen. I think one of them passed away last year. Just to look at this person here, he's a very serious looking person. He was Dutch, as you might imagine from the name van der Waals. He was awarded the Nobel Prize. And again, the same familiar patterns come. He left school, at the age of 15, which was pretty normal at the time. He then started apprenticeship. He became qualified, and then he did a bit of uni on the side. And then on the side, he also did some science contributions. I think eventually he wrote a PhD thesis, mainly in the area of thermodynamics. He came up with this correction and was awarded the Nobel Prize in 1910. And that brings me to the end of this lecture. So we've gone through in one lecture the gas pressures, mainly to calculate these things, apply the gas law. And that's it for this morning. Beautiful sunshine. I hope you're going to get a chance to stretch. And I will see you at 12:30 for the second lecture of today. Take care.
Thank you. Goodbye.
You're welcome.